conference in electrical and electronics engineering. The topic is smart materials, a choice for next generation flexible sensors and devices. So I belong to basically Sakraibiya. I'm working as a faculty member here. So the contents I will cover here: the background of IC technology, the flexible sensors based on the carbon nanotubes, energy harvesting sensors, and then conclusion. And if we have the questions, then we can address these questions. So the background of evolution of IC basically fabrication. We can see that this IC industry has been evolved from the vacuum tubes, and the first transistor was basically invented in 1948. And the first package in 1960, it was basically there were 4 transistors. They were mounted on a single chip. So then you can see in this image, we can see here there are basically billions of the transistor on a single chip. So this is how it has been possible in today's technology. So this is because of the Moore's law, and the feature size has been basically reduced, where we have basically fabricated a lot of transistors inside a single chip. This is because of the Moore's law, which states that every 2 years, the number of the transistor is going to be double. So nowadays, it is this Moore's law is also the challengeable, and a lot of things are basically being argued on this law as well as. So we can see here the device is scaling over the time. We can see here that the feature size, which was basically started from the 100 micrometer devices, and nowadays we are going to fabricate 0.1 nanometer devices. So it has been shrinked, it has been declined over the time. So we can see here that this area from up to the 0.1 micrometer, it is very easy, or it was an era of a simple scaling. We can fabricate the things at a larger scale. The size was very huge, and we can easily address the things. As we go down, so 1 micrometer, it is going to be the cell dimension. So the size has been reduced and the complexity has been reduced as well as. So in 0.1 micrometer, we can say the 130 nanometer in 2000 was the size of the basically devices which were basically investigated and fabricated. The scaling plus innovation area in this era from 0.1 micrometer to 10 nanometer, it is basically has been given by the ITRS, which is the international roadmap for the semiconductor technologies. And if we go down, we can see here in this 220, so 2020, 18 nanometer devices are basically being fabricated, and more than less than 18 nanometer basically devices are going to be investigated, and they are in the research. So this is the area we are going to be shrink again towards the quantum effects and then atomic dimensions. We are going towards the very low dimension. So we need to go towards the invention. What will happen in this area, because the size is basically is the atomic dimension. So we have to investigate these things. So as I say that the decreasing feature size, basically line width is going to be decreased. We are basically increasing the chip size. Wafer size is going to be increased. The circuit density is going to be increased. So of course the economical problems or the economics is going to be basically going to be involved, because once everybody is going to sell, or the Intel or the Microsoft AMD processor, they are building the processors. Of course they are selling the microprocessors, and this is why the economy is going to be basically is going to be affected. So we can see here in this basically image that line width versus fabrication cost. If the line width is going to be the fabrication cost is going to be basically is decreased. Okay, so we can see here it is going to be decreased. The fabrication cost is going to be increased once we are going to decrease the line width. We are going towards the narrow scale. The fabrication cost is going to be increased. In this way, we can say that once we do the medical in medical field, we are going to investigate the biological things like the DNA, what is the angiography, or we can say that the cancer problems, the cell or very minute level. We are going to have a sophisticated device, and these devices are fabricated of the electronic devices. So in this way, of course, the MRI and in experimental sciences, TEM, SEM, XRD, AFEM. So these techniques are very important in investigation of the low dimension devices. And of course, these devices are also very expensive. So that's why the cost is going to be is going to be increased once we are going towards the low dimension devices. So we can the challenge is having roadmap. We know the roadmap is very going to be challenging. And then truth is that there are a lot of still a lot of things are basically there in the fabrication of the devices. Once we do the fabrication, there are a lot of problems occurring. So there are 3 stages for development in the future. So technology performance boosters. So nowadays we are basically involving the materials, different materials and process innovations nowadays. So they are going to be fabricate source, drain, and the transistors, source, gate, and drain. So there's an issue with the gate and other deposition and the lithographic techniques. So we need a very thin gate. Gate is the heart of the transistor. So this gate should be fabricated of very smart material. So here we can see here the carbon nanotubes have been involved here. So after these 5 to 15 years of device innovations, so there the questions basically arise that how this gate or these things can be possible, because we are going towards these things. We need a spin-based devices, molecular devices, rapid single flux quantums, quantum cellular automata, single electronic devices, resonant tunneling devices. So what is going to be happen after the silicon? So because whole of the 95% industry is based on the silicon, so there should be the choice of the new materials. So what will be going to be happen? So flexible electrons concept is going to be arised here. We can see here from the silicon is a very rigid. We have to transform from the rigidity towards the softness. So these technologies should be transferred on the flexible substrate, and carbon nanomaterials are the very suitable choice for this one. So the sensors, you can see here in this slide, if the human in a human we basically implant a medical devices. So there's a problem on the skin, because skin is a very flexible. You need a power supply for these things. You need a power supply. It is very inconvenient in a daily life to replace the devices again and again, because these devices are operating on the battery. So it is difficult to recharge again and again battery and replace the things which are mounted on the human skin. And this will be basically going to be effect on the human skin, because human skin is a very soft. So you need a battery, because battery is a problem, because you cannot recharge again. There is a chance of the power supply wireless charging, so it is difficult for long time powering. So there's the concept of the flexible sensor. So you have to basically implement or improve the performance of the flexible devices, where we can have high performance, low power consumption, and self powering. We need these things. So first, flexible sensors, I have choose a carbon nanotube. We can see the flexible sensors. In the flexible sensors, you need strength sensors, because you have to stretch it, you have to fold it, you have to port it, you have to basically bend it. So the strength sensors, a lot of strength sensors has been reported by many researchers. This is the area where the graduate and postgraduate students can basically go towards their career, and they can do the research. The problem here occurs is this one. So the challenges are gauge factor, the hysteresis, the non-linearity. You cannot have a repeated basically this stretchable. So once you restore the things, you are not basically getting the accurate results. So there's still a lot of things are going to be done in this area. So the second basically the point is this: in the carbon nanotubes, why these are basically done or chosen, because their thermal electrical properties are very stronger than the copper and aluminum. Their strength is very basically very good than the steel. So that's why the carbon nanotubes are basically chosen, or one of the chosen material. So you can see
Sir,
here
please
this
conclude.
yes. So we can see here this is a flexibility. We can see that we have a great basically a report of the gauge factor, and then we can see these are the papers you can download, and you can go towards these things. So the devices PN junction has been basically fabricated from these carbon nanotubes by IR detectors and sensors. So devices have been fabricated. You can see once IR light is irradiated, you can get a voltage. The tanks energy harvesting for self-powered sensors can have been basically reported for many times, and these have basically the material wear. So material, they once they are getting with the good properties of silicon carbon nanotubes, you can have a great basically output over here. So measurement techniques, DAQs are basically involved. Electronic basically circuits are being used. So electrical distribution of the charges COMSOL is being used to investigate the things. And then you can basically calculate or measure the maximum power and the voltage. You can investigate these things by powering the small electronic gadgets and devices, and charge the capacitor that the things have been basically fabricated. You can use these devices as a self-powered sensors, because there's no need of the battery to charge again and again. You need a self-powered sensor. So this is a great area. So I will do the conclusion like this one. Basically, in basic invention between 1947 to 70 was basically because of the silicon. So there's a new era of the materials. So there's a basic invention of the new